Hello students, we are now studying part 4 of your Honors Geometry Summer Packet, Radicals. Feel free to take notes or just watch this video as a little refresher for you. The first thing we're going to discuss about radicals is reducing radicals. Typically in geometry, we do not put radicals into our calculator and get a decimal approximation. We prefer to simply reduce them. So before you can reduce radicals, you need to think about your perfect squares. So for example, 1 is a perfect square, and then 4, 9, 16, 25, 36, 49, and the list can keep going and going and going. Knowing your perfect squares is fairly essential to reducing radicals, because what you want to do is think about the largest perfect square that goes into your number. So if I'm thinking about 48, yes, there are lots of multiples of 48, but I really only care about the perfect squares. I know that 4 goes into 48. 4 goes into 48 12 times, but there might be a larger one. 9 won't go into 48, but 48 is divisible by 16. So if you think of the square root of 48 as just the square root of 16 times 3, you can then reduce your radical. All you have to do is square root each individual number. The square root of 16 is 4, because 4 times 4 is 16. The square root of 3 doesn't reduce, it is a decimal, so you leave it like it is, and that would be your reduced radical. Again, in honors geometry, we don't want to know the decimal approximation. The vast majority of the time, we want you to simply reduce it like this. So let's try another one. Let's think about 24. I want to know the perfect square that goes into 24. And in this case, 16 is going to be too big. I know 4 goes into 24. So ignore this 4 out front for a little bit. I can think of 24 as 4 times 6. And then you square root each individual number, the square root of 4 and the square root of 6. The square root of 4 is 2. The square root of 6, again, is not a perfect square, so we just leave it underneath the radical. When you have this 4 out front, it really doesn't affect your problem till the very end. This 4 is being multiplied to the square root of 24, so technically it's also being multiplied to 2 root 6. So all you have to do is multiply the 4 and the 2 to give you 8. So it would be 8 root 6. Again, when reducing radicals, think about perfect squares. Another common practice of radicals is rationalizing denominators. Because fractions are technically pieces of a whole, you always want a whole number in the denominator of your fraction. To get rid of the radical, which is not a whole number, all you have to do is simply multiply the numerator and denominator by that radical. And now watch what happens. I have 3 root 2 on the top, and then root 2 times root 2 is radical 4. Well, the square root of 4 is just 2. Now I'm into my piece of a whole. I have a nice whole number of 2 on the bottom, and I don't really care that there's a radical on the top. So this would be your answer. This is how we prefer to express it. Let's try another one. Again, root 3 is not a whole number. We need to get rid of the root 3 in the denominator of the fraction. So we multiply both numerator and denominator by root 3. So I have 15 root 3 over root 3 times root 3, which is root 9. So I have 15 root 3 over the square root of 9, which is 3. And then you want to stop and see if you can reduce your fraction. In the first one we did, we couldn't. 3 does not go into 2 evenly. But in this case, 15 is divisible by 3. 15 divided by 3 is 5. Now I can't divide the 3 and the root 3 because they're not really like terms. They don't really cooperate well with each other, as we say. So 15 over radical 3 is the same as saying 5 root 3. And now this one, just for example's sake, we have a big square root and then a fraction. First, you can always reduce your fractions. 10/6 reduce b 5/3, because both numbers are divisible by 2. And then, whenever you have a radical that looks like this, what you're basically saying is you square root the top and you square root the bottom of the fraction. And now we can rationalize. We will multiply the top and the bottom by radical 3. So I have radical 5 multiplied by radical 3 over radical 9. Since these are both radical numbers, I can multiply them and get radical 15 on the top. And then on the bottom, radical 9 is just 3. Now, I cannot reduce this fraction because the 15 is inside of the radical. So I just stop there. That's as reduced as I can get. We touched on this briefly when we were doing operations when we were reducing radicals. But now let's talk about just some basic operations. Whenever you're in a situation like this, where you have radicals multiplied to radicals, you can multiply the numbers out front together, the 5 and the 2. You can say 5 times 2 is 10. And then you can multiply the radicals together. So root 3 times root 6 would be root 18. And then, if you can, you want to reduce your radical again. So again, you want to think about your perfect squares. 4, 9, 16, 25, 49, dot, dot, dot. So looking at 18, 9 is divisible by 18, or 18 is divisible by 9. So you have this 10 out front. Think of radical 18 as 9 times 2. The square root of 9 is 3, and radical 2 cannot reduce. It's not a perfect square. So radical 18 is 3 root 2. This 10 that we started off with, again, it's just multiplied out front. So we'll do the 10 multiplied by the 3, so 30 root 2. And then for this one, since there's no adding or subtracting here, we basically just square each individual part. If there was some adding or subtracting in the situation, the problem would become a lot more complicated. But here, all we have to do is square the 5 and square the radical 7. Well, 5 squared is 25. That's fairly simple. Radical 7 squared, technically, you can square the 7, and it's still a radical number. Well, the square root of 49 is 7, so this is just 25 times 7. Which, when you multiply it out, 25 times 7 is 175. And that's all I have for you about radicals. So go ahead and practice your work in your summer packet.